Today we're talking about the dependent samples t-test. And a quick note about terminology. The dependent samples t-test, depending on where you're reading, is also talked about as the related samples t-test, repeated measures t-test, paired samples t-test, and matched pairs t-test. And the math behind all of these is identical. The only thing that's different is sometimes one of these terms might be more appropriate depending on the design. And the dependent samples or related samples t-test is what it is, right? The samples are somehow matched, related, dependent on each other. That being said, sometimes the samples aren't matched, for instance, because we literally have the same person twice. So that may not be the most appropriate term to convey what are we doing and why are we doing it. That being said, all these t-tests go by a slightly different name, but the math behind all of them is identical. The steps whenever you're going through performing this test are going to be the same as what you've seen in the one sample z-test and the one sample t-test. First, we're going to state the hypothesis, then we're going to select the statistical test, then we're going to check the assumptions, we're going to set the criteria for the decision, so that'll be the t-critical because we're doing a t-test, then we're going to compute the test statistics, so that will be t-obtained, and we're going to make a decision. So, starting with state the hypothesis. Dr. Arithmo thinks students will have higher SAT math scores after they complete a statistics course. Importantly, he thinks that they're going to have a higher one. So his hypothesis, the alternative hypothesis, is that the scores before they take stats, the mean is going to be lower, less than, the scores after they take stats. So on average, scores should be higher following the statistics course. Now, what this means is if we want to catch all other possibilities, right, we need our two hypotheses, the alternative and the null, to be mutually exclusive and include all the possibilities. Then the null is going to be that pre-stats is greater than or equal to post-stats. So maybe stats causes you to question your confidence in math. Well, because of that, maybe you actually perform worse after it's over. I really doubt it. I really wouldn't hope so. But those types of things could happen. Confidence is important whenever you're doing these things. We do see that if I put you into a group, if I put women, for instance, in a room full of men, whenever they're taking the SAT or the GRE, I can prime some stereotypes, and then we would have stereotype threat where they're kind of anxious about underperforming, and then that harms their performance. So we do see that it's not just your knowledge that results in your performance on a test, there are other things influencing it. That being said, Dr. Arithmo thinks that stats is going to help, thus the scores in the alternative, right, we see that the scores following taking stats are going to be greater than the scores pre-stats, and the scores pre-stats will be less than post-stats. We can then walk through and go, okay, well, what test are we going to do to compare this? Well, we have two conditions, right? So that puts us in either the independent samples t-test or the dependent samples t-test. So we have individuals before and after stats, that's two conditions. And we have the same people before and after. Thus, when we go, well, have we used matching, pairing, repeated measures? We in fact have used repeated measures, and we'll talk about more about that terminology in a moment. Also, quick note, we say sample to sample, but we can also think of it as condition to condition, and I've mentioned that before, but just a quick reminder. So we're comparing two conditions, people pre in that condition before stats and people post stats, which is our second condition. As I mentioned, one of the determining factors between independent and dependent samples t-test is really, do we have some form of related samples design? If we have a related samples design, we're going to end up doing the dependent samples t-test or the related matched pairs, matched samples t-test. Within related samples designs, we have two broad categories. The first is repeated measures design, and the second is with matched pairs. The repeated measures design We have the same person twice, so we have observed them in each condition. And we can have them across multiple conditions, in which case we typically just talk about it broadly as a repeated measures design or a within subjects design. Or we can have them before and after an intervention. So we only have 2 time points, like Dr. Arithmo has, and that's called a pre-post design. So a pre-post design is a specific type of repeated measures or within subjects design. We can also have matched pairs designs. With matched pairs designs, we have 2 people, one person is in one condition, one person is in the other condition, but they've been matched on some characteristic, they've been matched on some trait. So we can take the individuals and match them on a pre-existing trait, such as intelligence, or maybe we want to look at prior performance in math, for instance. That would allow us to have a matched pairs design. So we would take everybody and rank them based on, let's say, their SAT in high school. And the top 2 people would then be paired together. One person would take stats, the second person wouldn't take stats, and then we would look at their SAT scores after they had taken statistics. So one person took stats, the other person didn't. They take the SAT again, and then at that point, we can decide, well, did the person improve? But before we ever started, we matched the individuals on their SAT ability, their SAT performance. The second design is where we have participants and they're matched based on some type of existing association or a natural association, a natural relationship. So an example of this would be siblings. Siblings tend to go to the same school, their parents are similarly educated, and so because of that, they share a lot of history in terms of their experience, their exposure to something such as mathematics, and because of that, they should be somewhat alike, somewhat similar. And so if we then randomly assign one sibling to take stats and the other sibling to not take stats, that matching helps us to account for some of the variables that might also influence SAT performance, like how good was your high school, and did your parents have a lot of books in the home, were your parents well educated, which we also know impacts these things. Importantly, what all of these related samples designs do is they remove the importance of between person error. So if I'm a good test taker in a related samples design, especially a repeated measures design, it really doesn't matter that I'm a good test taker. I'm a good test taker when I take it before stats. I'm a good test taker when I take it after stats. So all we care about is the improvement. So assuming that I was a good test taker at time 1 and time 2, that is probably influencing my SAT performance, but it's influencing my SAT performance at both times. Thus, that ability, that natural testing ability, or maybe it's testing ability that I've developed with time and practice, but either way, that can't be the determining factor. It has to be whatever happened between time 1 and time 2, which is the stat scores. We could also walk through this type of test selection. It gets us to the same answer. So we ask ourselves, what is Dr. Rithmo doing? Is he comparing groups or checking associations? Well, he wants to see if students will have higher math SATs after they complete stats, right? So we're comparing groups. In fact, we are comparing conditions. So individuals, when they are ignorant of statistics, right, that's a condition. And then after they've been introduced to statistics is our second condition. So in this case, we have 2 conditions, 2 groups, not really samples, because we have 1 sample and under 2 conditions. Is a repeated measures or matched pairs design used? Well, yes, right? We're testing the same people before and after stats. Because of that, the samples, really the conditions, are dependent on each other, related to each other. You don't get much more related than yourself. And because of that, we would do a dependent samples t-test or a related matched pairs t-test. Now, for this test, we have two important assumptions. The first is normality, and then the second is independence. And you've heard about these before, but the way that they play out in a dependent samples design is a little bit different, because now we're not worried about normality within our original scores. So we don't care if SAT at time 1 is normal or if SAT at time 2 is normal. What we care about is when I take the individual's score at time 1, subtract their score at time 2, are the different scores, when I do that for all people, are those different scores normally distributed? Similarly, independence is a little bit different because now I don't expect that when I test a person at time 1 and time 2, their scores are independent from each other. That's not tenable. That's not a good assumption for this test. In fact, we assume, that their scores are dependent. They are related to each other. So it's not about are the scores independent, right? Within any condition or within any group, the scores should be independent, meaning that the different scores should be independent. So a person from time 1 to time 2, their score is going to be dependent, but again, across the people, between people. Now, can we fully answer that from the way that it's stated? As we've discussed before, sometimes you need a little bit of extra information. Now, we do know that the SAT is a normed test. It's a standardized test. Those tend to be normed in a way that they have a normal distribution. So probably we're safe assuming that. For independence, though, we would need to know how are we getting these SAT scores? Where are they coming from? Are the people tested individually? Those types of things. Is there any way that within a group the people could influence each other? So once we've selected the test, once we have gone through, checked our assumptions, made sure that this test is appropriate, then we want to set our criteria. And again, for a dependent samples t-test, when we say set the criteria, what we're really talking about is the critical value of t, so t-crit. So Dr. Arithmo thinks students will have higher SAT math scores after they complete a statistics course. I've added in alpha, so we need to know that in order to set the criteria. Here, alpha equals 0.05. He asks 30 students to complete the SAT math test before starting his statistics course in the fall. At the end of the semester, students complete another version of the SAT math test. Importantly, when we write it out this way, we see the number of students, which we're going to need to know. We see that we have the students completing it before and after, so now we get a sense about the fact that the students are dependent on each other. And then we can use that information along with the critical values of t, and this is provided to you, but you also can find it in SPATS, Appendix C, Table D on page 388. So this critical value of t table, we need to know a few pieces of information. First, for our alternative hypothesis, is it directional or is it non-directional? Is it one-tailed or is it two-tailed? Well, when we see that pre-stats should perform worse than post-stats, that lets us know that it's one-tailed. We're interested in one direction. So we know that we're focused on this row here, where they're all one-tailed. We also know that alpha is 0.05. That tells us what column we're in. So we're in this first column of critical t values. And then the last thing that we need to know is degrees of freedom. And in a one sample t-test, degrees of freedom was n-1. In a dependent samples t-test, we're focused on different scores. So it is nd-1 because we have to calculate the mean for the different scores. And we've talked before about that means that whoever's different score is the last in the calculation, we have to constrain it such that we get the mean that we're supposed to, thus that person's score is not free to vary. Importantly, we have 30 students taking the test before and after the stats course. Well, technically that means we have 60 SAT scores. But again, we don't care about the original scores. All we care about is the difference scores. So if Billy took it at time 1 and Billy took it at time 2, I don't care about Billy's score at time 1, Billy's score at time 2. I care about the change from time 1 to time 2. I care about the difference between time 1 and time 2. Because of that, I'm going to have 30 different scores. So my degrees of freedom is going to be 30 minus 1, which is 29. 29 is between 20 and 30. We could go find a table that's more specific, but it's going to be somewhere between 1.73 and 1.70 is our critical value. So we really only need to worry about a more specific table if our obtained value happens to fall between 1.73 and 1.70. Using this more conservative value of 1.73, if our score is rarer, our obtained value is less likely, less probable than 1.73, whatever the real value of the critical value is, it would be significant at that point too. Now, importantly, when we think about the alternative, we can think about the alternative instead of just pre-stat is less than post-stat. We can think of it as, well, if pre-stat is less than post-stat, when I say pre-stat mean minus post-stat mean, I should find that the pre-stat mean, if it is less, when I subtract a larger number, right, because post-stat it should be higher, I should end up with a value that is less than 0, a negative value, because if I subtract a larger number from a smaller number, I end up with a negative value. So this 1.73 is going to be on the left-hand side of the distribution. So it's going to be negative 1.73. What that then means, when we get ready to do the decision, is my t obtained, where is it? Is it to the left of this? Is it less than this cutoff value? Is it more extreme? Is it rarer in the correct direction? If it is, that would be significant. However, everything at negative 1.73 or to the right would be non-significant, which we often note as just NS. So we now have the critical value. We need to know the obtained value so that we can compare those two. So Dr. Rithmo thinks students will have higher SAT scores. We've already read through this. To get the obtained value, it's actually very similar to the way that we got the value for one sample t-test. So in the one sample t-test, we take the mean of the sample, we subtract the population, we then divide by the standard error of the mean. And the standard error of the mean is the variance divided by n. We take the square root of that quotient, or we can take the standard deviation, divide by the square root of n. Both of those give us the same outcome. With the dependent samples t-test, the formulas are very similar, except now we are focused on the difference scores. So now, instead of the mean of the sample, it is the mean difference within the sample minus the difference in the population or the expected difference in the population, and then we divide by the standard error of the mean difference. So the only real difference is we have to calculate the difference scores first. Once we do that, we use the difference scores as though they are x, and we walk through every step the same way that we did before, and I'll show you that in Excel in another video. So how does this process of calculating the difference scores work? We have individuals and their scores at the pre-stats time. Also, sometimes people will refer to this as T1 or time 1. We also have individual scores after stats, post stats. Some people would refer to this as time 2 or T2. To get the difference score, all we simply do is subtract post stats from pre-stats. So 530 minus 536 gives us negative 6. 580 minus 583 gives us negative 3. 670 minus 671, negative 1. 650 minus 654 is negative 4. And 480 minus 504, negative 24. Importantly, like I said, We only care about these initial scores in order to get the difference score. Once we do that, these are the scores that we care about. What this does for us, again, if somebody's an awesome test taker, I don't care. That's not important. What I want to know is, does stats help them? And does stats help awesome test takers? Does stats help poor test takers? Does stats help individuals regardless of test taking ability? Does stats help individuals regardless of their prior math background, the level of high school that they went to, how good that was, their parents' education? All those things are controlled for because I have the same person twice. So if you went to a good high school, at time one you went to a good high school, at time two you went to a good high school. If your parents are math whizzes, at time one they were math whizzes, at time two they were math whizzes. So all those individual differences, I really don't care about them. They get pulled out of the model. They're not included in the scores because all I care about are the difference scores. How does your score change by having exposure to statistics? We then use these difference scores to calculate our average difference, our mean difference. And you can see here it's same as calculating the mean score, except now we're going to sum together all the different scores. So I'm just using delta, which is often used to represent difference, so the Greek letter delta, which looks like a triangle. I'm going to sum delta, so -6 plus -3 plus -1 plus -4 plus -24, and I would continue until I got to the end of all the participants. And then I'm going to divide by the number of difference scores in order to get the average difference. Before, we added all the x scores, right? Then divided by the number of x scores. Well, I could just as easily put sum x instead of sum difference, but I think this helps you to see that really the only difference between what we were doing before and now is we have to calculate the difference scores before we even start. Now, once I have that, x bar d, the mean difference, that goes into the t obtain. And then I also need the standard error of the mean difference. Well, the standard error of the mean difference is about the variability or standard deviation of the difference scores. So we've seen and calculated standard deviation before, where we take x, we subtract the mean, we square it, right? So we get those squared deviations. We sum those all together to get the sum of the squared deviations, or the sum of squares. It's often referred to as that as a shorter form. And then we divide by n minus 1 because we're working with a sample still. Well, the standard deviation of the difference scores is going to be the same general idea. We're going to, for each difference score, subtract the average difference score, square that to get the squared deviations around the mean difference. So how far is -6 for this first person from our average difference score? For the second person, how far is -3 from the average difference score? So we take each individual difference score, noted here as delta with a sub I. Again, that I is just an indicator to help remind you that we are doing this for each individual person, and we're going to have to keep track of that. And the I would then become 1 and 2 and 3 and 4 as we move from participant 1 to 2 to 3 to 4. We before have even seen in the original SD where it's sigma xi minus x bar, and I talked about how a lot of the times I leave that I off, and you will find that in later times when I present the equation for the standard deviation of the difference, I leave the I off again. But we're going to add together those deviations around the average difference and then divide by the number of difference scores minus 1. Very similar. All we have to do is remember, calculate the difference scores, use the difference scores as x, and everything from there on out is the same. This last piece of t obtained. So now we know what x bar d is, where it's coming from. Now we know what the standard error of the difference is and where that's coming from. Well, this last part, mu d, often depends on the expected or actual difference in some population. Well, a lot of the times, theoretically, conceptually, we're not really worried about that. So we think that SAT is going to improve, right? We think that that difference is going to be less than zero. Well, if there were no difference, right? If stats didn't help, in that hypothetical population, the population average difference from time 1 to time 2 would be 0. Well, if I'm subtracting 0, I can just ignore it. Now, that's not always the case. Let's say that I have a new treatment and I want to say, we have these individuals, they have depression, we measured depression at time 1, we gave them this new therapy for 6 weeks, and then we measure the depression at time 2, and I want to see how that change looks compared to if individuals came in with depression, take an antidepressant medication, and time 2. Well, whatever the change is with the medication being present, we could use that change as mu d, and then with the new treatment, the change would fall in for x bar d for the average difference for the sample. That being said, for the most cases, we don't have that comparison. We don't have a population of comparison, and because of that, it often is the case that this mu d is just going to be 0 unless I provide it to you or specify it. So if it is 0, we can just get rid of it. We can simplify our formula, because if I subtract 0 from any number, I'm just going to get that number, in which case I can just say x bar d divided by the standard error of the mean difference. The last thing that we can calculate is the confidence interval. So confidence interval, similar to what we saw before, now it's going to be x bar d, so the average difference plus or minus t critical times the standard error of the mean difference. Again, when we add, we're going to end up with the upper limit. When we subtract, we're going to end up with the lower limit, assuming that we always use an absolute value in t, which in this case, it actually is important because our value of t was negative 1.73. If I multiply by negative 1.73 times the standard error of the mean difference, I'm going to get a negative number. If I add a negative number, my upper limit would actually end up being smaller than my lower limit. They actually would flip places. And when you look at it, intuitively you'll go, wait a sec, this is the smaller number, that has to be my lower limit, this is the larger number, that has to be my upper limit. So you probably would catch it. But if you always use the absolute t critical for this calculation, then you add, you get the upper limit, you subtract, you get the lower limit. Now, the way that we're using those, we have x bar d, whatever that average difference is, and we're going to walk through a concrete example in Excel here in a moment. But whatever that average difference is, if we resampled, if we got a new group of students, they took stats, well, they wouldn't have the same exact average change, they wouldn't have the same exact average difference. We need to know where would that fall, right? So thinking about that sampling distribution, if we resampled, what sample means, in this case, what sample differences would be likely. And we can use the lower limit and the upper limit to set a range for those values. So it should be that the mean difference isn't going to be exactly what it was before, but it's somewhere between the lower limit and the upper limit. Importantly, we anticipate, right, Dr. Arithmo thinks that this difference is going to be less than 0. If the difference is less than 0, and that's our expectation, if the lower limit and upper limit don't include 0, and specifically because it's directional, even the upper limit is less than 0, it would suggest that our average difference is significantly less than 0. That's consistent with the alternative, thus we would reject the null. Which brings us to step 6, where we have to make a decision. And we can make this decision using null hypothesis significance testing, using that t obtained compared to the t critical, which is what we see here. So if t obtained is less than negative 1.73, it's significant. We reject the null. We can also use it with confidence interval, where if we create this confidence interval around our mean difference, and the range, the lower limit to the upper limit, is less than 0, it would suggest that the difference is significantly less than 0. Thus, the change from time 1 to time 2, scores are increasing from time 1 to time 2. Students are performing better on the SAT at time 2. And SPATS goes more into those confidence intervals and how to use them. So if you're still not sure about them, feel free to go to the textbook, read about that, because he actually focuses more on that than the null hypothesis significance testing now. So again, if 0, in this case, because it's directional, is larger than the upper limit, we would find that it is significant in that case as well. And it should be that our results for the null hypothesis test and for this confidence interval, they coincide with each other, they concur with each other